All right, we're moving into the last section of the class. It's really exciting, actually. So, we've been doing all this stuff, just kind of moving back. This was L'Hopital's rule from last class. Everything we've been doing in the last, 3 or 4 weeks, derivatives. All right, derivatives, built them up, first and second derivative test, optimization, related rates, all that stuff's been derivatives. We're moving out of it, and we're moving into something else. This is the last section, and it's unfortunately going to use the word derivative. It's going to be involving antiderivatives, but at least the idea is we're not progressing further into this thing, right? We've kind of hit the apex, I would say, and we're coming down the slope on the other side. A little bit of encouragement. And the idea is we're going to think about first estimating the area under the curve. That'll lead us into the next concept of antiderivatives. And so here's sort of the main question I want to focus on today that we're going to estimate first is, how do we add up total amounts of some function, right? Derivatives tell us rates of change, and we can do great things with them. I hope you'll agree that we've solved some interesting problems by thinking about rates of change. So instead of rates of change, how do we add up total amounts of a function? For example, didn't do that. For example, let's say we've got this function and it tells us the number of births that are taking place at a certain point in time. So it's like a birth rate kind of function. And we want to know how many births have taken place past some interval or between two numbers or something, right? So from A to B, for example. We would basically want to add up these individual function values over this interval, right? And so let's draw a picture real quick and then we'll understand what we're talking about here. So I'm going to try to draw the same picture twice. One's going to be the exact value and the other is going to be the estimate. And so let's both try to draw the same thing twice. Try to draw kind of like an extreme x squared value, or maybe almost like exponential looking. So something that's kind of like this. And try to draw the same thing twice. And so this is our birth function, right? This is our f of x. Tells us how many births are taking place, and x is on the x-axis, of course. And so the births are going up, right? We're having like more births. Most populations, especially human populations, are going up. The birth rates are going down lately. And I think I read I think it's Japan who actually had a negative birth rate for the first time recently, which is pretty unheard of for humans. Anyway, so that's our birth function. I didn't quite do it the exact same way. Oh, I should have taken advantage of my ability to copy and paste this thing. I think I'm going to try that. No, I'm not going to try that. It's going to take too long. Okay, so we got the same function, and we want to do the birth between 2 points. So I'm going to label that A to B. So make A kind of pretty far to the left, make B over on the steep part of this thing. Maybe right at the end of it. So, every single point on that line, which I'll just kind of do a couple of dots here and then I'll erase them, but every point I've just dotted on that left line tells you the number of births that are coming out of the time. So if we want the total number, we would want to add up all those points. But points, there's infinitely many points between A and B. Right? Think about that for a second. I know it kind of looks like, oh, you just drew a couple of them, and if you filled it in, you get them all, right? But between any two numbers, there's infinitely many individual points. So we can't just like add them all up. But what we want is that area. We want each function value, which in essence is telling us this area. This is going to be what we want to determine. Try to fill that in best you can. I guess I can cheat a little bit and do this. And this is the exact value, of course, right? If I could somehow do this area, we'd be in business. But it's like not a normal shape. If it was like a square or a rectangle, we'd have formulas for that. But we don't know the formula for this shape, right? And so this is the exact value. So I gotta make my thing again. But we need advanced techniques really to do that. And so we're going to learn about this in the next section. But that's really what we're after. And that's what I always like to start with, is like, this is eventually what we want to do. And actually by the end of class today, I hope to kind of introduce the idea, but we want that exact area We're not quite ready for it. And so what we do in this section is what I'm going to show you on the right, which is to approximate the area. And so the very classic thing we always think about and usually leads into the next step, because we take a limit, so we kind of connect it to past concepts. Anyway, is thinking about, okay, well, I don't know the standard, I don't know the formula for this shape. So let's just come up with a formula of a shape we know, like a square, for example, or a rectangle, and estimate it with a bunch of rectangles instead. And so in this section, what we do is we estimate it using area of rectangles. In case people are still drawing that. And so instead of getting the exact area, which we'll kind of get to next time, we're going to think about, okay, well, what if we just estimate this by putting a bunch of rectangles underneath there? And so let's see what that looks like. Let me get another color out here. I'm going to take my interval, A to B. Let's break it up into a bunch of equal sized pieces, and then we'll put a bunch of rectangles underneath there. All right, so that's, maybe I'll just make that note here. I'm going to break up into n, and in this case, well, let's see, I'm not sure how many we'll do. N equals something equal size pieces. How many can I get in there? Maybe 3 or 4. Let's find out. Maybe like 1, 2, 3. So I drew 3 lines, but there's 4 actual pieces, right? Oops. So there's 4 pieces right there. And I'm going to label them. A is going to be the starting point. The first one's going to be x1, x2, x3, and then the last one is x4, right, the ending point. So you can see there's going to be 4 pieces there. And that's going to be the base of our rectangle. And I'm trying my best to make them equal size, right? And then notice how if we stick some rectangles under there, we can make either side touch the top. I'm going to make the left-hand side touch the top. And so here's my first rectangle. Here's my second rectangle, third rectangle, fourth rectangle. And so I'm trying to use the notation from down below. If you scroll down and you look at your own paper there, n equals 4 is going to tell us how many rectangles do we have, right? And so you can see I've got 4 rectangles right there, but notice how there are 5 x values, because if you want to have 4 rectangles, you need to have 5 pieces, right? Excuse me. And the other thing I'm kind of pointing out here is we want the exact value, which is on the left. This is an okay approximation, but it's certainly a bunch of error in here, right? If I kind of zoom in on this and I think about, well, I really wanted to get right up to the graph and all this gap, and the gap gets worse as the graph goes on, right? Look at this last gap. This is a huge gap that we're missing right here. This is what we would call error. We wanted that in part of our calculation and we missed it. And so something we're also going to talk about is how do we minimize error? That's a huge topic in sort of advanced math and just general, anything really, especially computing if people are in computer science, minimizing error, right? Making things optimal. How do we get that error down, right? So we'll talk about that as well. People have any thoughts about how we can get that error down? We'll write it down later, but ideas? Maybe just plant the seed if no one wants to contribute that idea now. Maybe think about how would we make that red part smaller? Right? What are some things we could do that wouldn't do that? Anyway, we'll keep going here. I'll get we'll kind of formalize this mathematically, and then we'll do an example. And then I hope to, based on the time, I think we might be able to start the next idea and kind of, I don't like to spend too much time in this. It's like this fake estimate thing that eventually we're just going to say, yeah, forget that and let's get the exact value. I like to set up the idea, but not waste a ton of time on it. Yeah, so a couple ideas to minimize that error if we want to make that error smaller, and we'll write this down at the bottom. But yeah, either adding more x values, so maybe more rectangles is what I'm hearing, right? If you have more rectangles, you can get kind of closer up into the graph there. Smaller rectangles and squares, yeah, so same idea. Maybe another idea that, well, you can think about, I'm not going to show you it, but another idea is a different shape, right? So rectangles are a shape that we're using because we know the area, but maybe there's a better shape we could use that we also know the area of. For example, trapezoids is the other one. A trapezoidal rule is a different one. Anyway, we can make a couple of those notes down at the bottom here. All right, questions about anything I'm trying to say there before we formalize this? It's good to get. And this is kind of the difference if we're talking about the quiz we just looked at, the difference between getting the idea of something and then actually writing down the math part of it that carefully lays it out, right? So for example, saying, I want all the side lengths to add up to 10, or the area of the sides adding up to 10 is one thing, but writing down what that means in terms of the actual math isn't more important. Okay. And so the key idea here is the thing we've just been working on. We've just added up a bunch of function pieces. And so here's how we do it mathematically, right? This is formalizing mathematically. It's always going to be these 3 steps. The first step is always to just break up the interval a to b into different pieces. And we define what the x values are, just like we did in the second ago. And then we're going to add up each function value and multiply it by delta x. And let's talk about that in a second. Let's do these step by step here. So the first one, right, this first thing is sort of telling us b minus a over n is going to be the end point minus the start point, right? So you're figuring out the width, and then you divide it by the total pieces. And that'll tell you how many x values you have. Or I'm sorry, that'll tell you the step size you want to take between them. Right? You want to think about this as like a step size. And then we step along. So notice how this is a delta x thing, right? I didn't mean to undo that. I wanted to erase that. Right, so we're calculating delta x here, and then delta x gets used in all these locations. Right, so you sort of take a step of delta x from the beginning to the end piece is what this is saying. I think sometimes it helps maybe to draw a slightly different picture here. So it's like, let's do a linear picture. You start with a, that's your x0. You're going to end with b, that's your xn, right? So your first point and your last point. And the way you get between them is by taking size steps of delta x, right? And so you'll have like x1, x2, x3, dot, 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 xn minus 1, all the way to the last one. And what I'm trying to point out here is when you walk from one step to the other, it's size delta x. Oops, not the last one. There we go. I know this looks complicated with, if I didn't have the picture there and you just looked at this thing that says x1 equals a, x2 equals a plus 2 delta x, that looks confusing. And so if you just have this picture, you're just saying, oh, we're just kind of like walking along size step delta x.
How do we know how many ends we should, or how many pieces we should divide it into?
Yeah, so in terms of like practically speaking, the problem will just say, hey, use this many pieces. Like for example, we look at this example here. It says let n equal 10. So it's one of the things that's given. And if you were going to choose it, you would just choose a random. You'll never have to choose it yourself, though. It's always part of the problem. Yeah. Okay, and so then we want to add up the area of a bunch of rectangles, right? And so that's what the next part says. Step 3 says, then we want to add each function value at each point and multiply it by delta x. That's because the formula of the area of a triangle or a rectangle is base times height, right? And so leave a bunch of space here, but just kind of on the side here, let's just draw a generic rectangle. Maybe this is at the point x1, x2 or something, right? The base is, if we wanted to know the width of the base, it's going to be delta x. Whatever delta x is the length of the base. And then the height is the function value. And so the area of this thing is the function value times delta x. And so that's why when you see this thing down here, or here for that matter, you're adding up a bunch of function values times delta x, right? Base times height. So you're adding up the area of a bunch of rectangles. Now I'm going to draw a couple more pictures in the middle here, so it'd be good to leave some room, or maybe you can have another page or something if you want. But I'm just trying to explain these formulas so far. These are adding up base times height of a bunch of rectangles. Now, I'm just going to try to draw that same picture again, I guess. Notice how there's two options here, right? There's this number 1 and number 2. And what I want to do is draw two pictures that sort of show what each one of these things are doing. I always debate, like, should I just put these pictures right on here? And I usually think, like, there's some value in having you actually put pen to paper on these things to write it out, kind of experiencing a little bit and seeing, like, oh, these are the different x values. We're taking steps of delta x, etc. Anyway, so I'm going to try to rewrite that same thing we just did a second ago. Let's get it set up. Let's not quite finish it. So we'll go from A to B again. And we'll do, and I did not do a good job of doing the same number of steps. Let me make that a little bigger. We had 3 intermediate steps, right? 1, 2, 3. Okay. So we started at x0. This is x1, x2, x3, x4. All right, let me stop right there. What's that x before the b? Can you clarify? So someone in the chat said, what's that x before the b? I'm not sure what you mean. x3? Is that what you mean?
I think he meant x minus 1 in the example before. I mean, n minus 1.
Oh, this thing right here.
Yeah.
This is, so I was counting up. So this is, notice how I've got like this ... thing here? Okay, yeah. So this is like common math notation. It's like, we don't know what n is, so I don't know how many x's there are here. And so I'm trying to do an example of like, oh, well, the first one's, or the 0 one here, the first one there, the second one here, the third one here. And then there's some amount in between, right? And then this is the last one. And so what you write to represent the one before the last one is x sub n minus 1. So that's what that says. It says the x value 1 before the last one is the way you think about that, n minus 1. Sorry that I know it got a little, there's a dot underneath it, which is confusing there. Other questions? Okay, so what I'm trying to set up here is everyone's set up to watch this, because it'd be good if you looked at this, right? So there's 2 different formulas, right? One I have labeled number 1, one I have labeled number 2. The difference is when you write rectangles, you need to decide whether or not the left top of the rectangle touches the graph or the right top. Like in the example I did up here, notice how it was all left top. So I'm going to highlight that a little more in blue. right? The blue dots I'm kind of writing in there. The top left of the rectangle touched it, and therefore we had an underestimate. And so let's just kind of remind ourselves about that situation. That looked like this. When you have the left top touching, it looks like this. Right? We have 4 rectangles. The left top is touching. It's an underestimate in this case. Right? We have all this error between the graph and the things that we wanted to capture. We really wanted that error. And so this ends up being an underestimate of the actual area because we have that missing pieces there. Right, so this is the same thing we just did, just kind of reminding ourselves. What I'm trying to point out here is if we let the right top touch the rectangle, it'd be a perfectly fine way of doing it, but then we'd have an overestimate. Right, so let's do the same thing, but instead of having the left side do it, let's make the right side touch the graph. So we still have error, right? So now the error is above the graph inside the rectangle. And so we added up these rectangles, our estimate would be too much, right? This would be an overestimate, or the other one is an underestimate. And the point I'm trying to make is it depends on whether or not you use the left or right endpoints paired with the shape of the graph. That's important to note too, right? It happened to be over and underestimate in this case because the graph was going up. If it was going down, it would be the opposite case. But just knowing that one is going to be over and under is what I'm trying to point out here. I let people finish writing this down here. Let's see if there are questions about what I'm trying to say. And I see someone says, wouldn't you be able to solve for that gap if we're using the top left be the height when it's touching the graph? Wouldn't you be able to solve for the gap if you are using that? Can you clarify what you mean by that, Sebastian? I'm not really sure what you mean. Yeah, go ahead.
I thought about it as like, if you're gonna use the left point as the height, those all just look like a whole bunch of right triangles.
So I see. Like, couldn't
I
you
would
figure out
assume
what
you'd
those
just be
things
able
are?
to solve for that like gap in there, and then you wouldn't have the error no more.
Yeah, that's an interesting point. So your point is you've got like you'll end up with a bunch of things that look like right triangles, like these things. And so can you just like figure out what those areas are and then figure it out? Yeah, that's a good idea. And actually, so first note that they just kind of look like right triangles. It's really a curvy graph. And so it's going to be, that's not straight. And so it's still going to be an estimate, even if you were able to do that. And you're actually getting at the idea of what the trapezoid rule does. So the trapezoid rule, instead of putting rectangles under there, it puts trapezoids, which do this. And so the top kind of goes at an angle and cuts off the error a little bit. So it kind of incorporates, in some sense, the triangle into the top of the graph. So that's what's called, I'm going to erase this in a second, but if you're interested, I'll write it actually on a different page. It's called the trapezoidal rule, I think. I think there's an AL on the end of that. And it's like a better estimate. But all these things are just estimates. I don't want to, sometimes people kind of go into that and do different estimates. I'd rather just get to the kind of the exact value and not spend too much. But yeah, that's a good thought. And the trapezoidal rule does just that. Yeah. Other things, that's a good thing. Other thoughts like that? It's also only a triangle in this case because of the way this particular graph is shaped, right? If the graph was shaped some different way, they may not be a triangle in the gap there. Okay. Other things? So notice n is 4 in this case. I just want to kind of clarify that. We could have more rectangles. We just have 4 in this case. And what I'm trying to point out as a reminder as well, red in this case is the error. Right? You're either getting too much or too little, depending on whether or not you use left or right endpoints. And so here's how we actually formalize that, right? Down at the bottom, you guys seen this notation before? We haven't seen that in this course, I don't think. Do you know what that means?
The sum of?
Yeah, so this means the sum of. Kind of write it off to the side there. And so we're doing the sum of, and then the I equals 0 to n minus 1 part, that means you're taking I and you're moving it between 0 and n minus 1. And notice where I is, right? I is here, and then it's also here. Right? So if we kind of write out these terms, this is going to be F, and you can, delta x is multiplying it every single time. Let me actually start there. It's multiplying it every time. The thing that changes is the F part. And so you can actually just factor out the delta x, and then you don't have to write it the whole time. Hopefully that makes sense. And then, right, so I goes from 0 all the way to n minus 1. So I'm going to do that same notation, dot, 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 all the way to the second to last one.
So did you do any estimating the area under the curve, any stuff like this in your pre-calc class?
No.
No? All right, because I know I didn't have you, but I must have done this in high school because it looks very familiar.
Cool. That's great. Yeah, I didn't do that in mine. It's possible people do that. I actually just started looking at a different pre-calc course of this online thing that I was looking at, and the stuff they do in pre-calc is very dependent on the school, is what I've kind of seen. Pre-calc isn't super defined. Usually it has some trig in it and some form of algebra. But anyway, people see what I'm doing there. So on that particular one, notice how you start with the first one and you only go to the second to last one. And that's what happens here. You go to the first one and you end at the second to last one. Where the next one is going to do the opposite. It's going to start at the first and go all the way to the last. Right, so if we write out the second formula, get a different color here. This one's going to be delta x. Notice how n starts at 1 and it goes all the way to the last. So we're going to have f of x1 all the way to the last one. All right, we're going to do an example here. Just a moment. Any questions before I slide down and look at that example? We'll relate it back to this steps in a second here anyway. So, all right, so we're going to actually do this exact example. So the curve I've been drawing is just generic, but it could be the curve x squared plus 1. Right, and so if you think about x squared plus 1, it does this. And so it kind of looks like the right-hand half of that. And we're going to go from 0 to 5. And so we're going to kind of look at the same kind of piece of a graph we're looking at, right? And so that's our A and our B. And so we're just going to break up the interval, plug in the points, get the estimate. And notice how it's telling us to do both upper and lower sums. That means use right and left endpoints. And I actually didn't label that in my last thing, did I? I think I need to label that. Don't really have room to label it. So I'm just going to throw this label right here, unfortunately. So the first thing I did is left endpoints. That's this thing right here. And then right endpoints is the other one. I can slip that underneath. Right, remember again, it's like, does the top right touch it or does the top left touch it? The first thing we did was the top left. The second thing we're looking at is the top right. And we're just going to kind of do both of them. And we're going to write all the function values down and basically you just choose, do you use all of them? I mean, do you use the right hand half or the left hand half? Anyway, you'll see it in a second here. All right, let's set up the problem. So we're going to do steps 1, 2, 3. 1, 2, 3, right? So first thing, break up the interval. We're going to use 10 pieces in this case, and so it's going to be a little bit longer, but we're going to get a good estimate. And so number 1, figure out the step size. It's just b minus a over n. In this case, b and a are 5 and 0. So 5 minus 0, right, in the top there. And then we're being told to use 10 pieces. So n is 10. And so all that tells us is, we get 5 over 10, of course, or 1/2. That just tells us the step size we want to take between the x values is 1/2. And so, we're walking from, the other way to say that is, if you wanted to take 10 steps between 0 and 5, they have to be size 1/2. And so you don't even need a formula to kind of think about that. How many step sizes do I need to take to get 0 to 5 in 10 steps? Well, 1/2. And so that becomes the second piece. What are the x values? Do you need to write this down? Do I need to see this? No, but I'm trying to be clear about how this works. How do you formalize these things mathematically, right? So x0 is the first starting point, which is this case is 0. And then we're just going to take half step sizes all the way up to 5. Right? So x1 is going to be 0 plus 1/2, which is 1/2. I'm going to try to write a little bit better. x2, just take another step size. Just keep on stepping along all the way to the very last point, which is 5. So hopefully you're with me that each one of these delta x, you're doing delta x equals 0.5. Delta x equals 0.5.
What is x2 equal to?
You tell me. If we started at 1/2, right? x1 is 1/2, and then we take a step size of 1/2, what do we get to? We're just taking steps of size 1/2. So 0, 0.5, 1. Oops, I just said it. 1. Right. So this says 1/2 plus 1/2. Maybe that's what your question was.
Yeah, thank you.
Right, we're just kind of breaking up the interval. Other questions? Okay. So oftentimes when I'm in person, I will show people how to kind of calculate function values quickly on a graphing calculator. If you have some trick you like to use to do that, that'd be fine. I usually don't involve questions on tests or things like that, but I'm just going to make a quick table. I did this ahead of time. And if it's not clear what we've done so far, the x values are as follows, right? We started at 0, and we're just taking steps of 0.5. So it would be like 0.5 is the first one, then 1, 1.5, 2, 2.5, 3, right? We're just step sizing 0.5 all the way up to the ending point. And we need the function values, right? We're going to plug, you want the heights of all the rectangles. And so I just did this ahead of time in my calculator, and I got all the outputs from these locations. You just plug it into the formula. And I got as follows. And we're going to use all of these for different parts of this. And so I thought it'd be good to just have them all written down somewhere. So this right-hand column that we're writing down right now, I obtained by plugging the x values into the function. And I'm going to be real tedious about this one example because I want it to be totally complete when you're looking at it later. Because the third step is to do the three formulas or the two formulas. So that'll be step 3. Let me just pause there and see if people have questions or need to catch up. Chat looks clear. All right, so let's do the two formulas, right? So there's two formulas at the bottom of this page that we kind of wrote down. And we'll do 1 and 2. And so it's either left endpoints or right endpoints, right? So the first one, if we wanted to use left endpoints, which is going to end up being an underestimate in this case, the area between the function and the x-axis is approximately that formula, right? So that formula was delta x times f of 0, 0.5, all the way up to the second to last one. This is the first one. This is the second to last one. And so if we're thinking about the chart that we just drew, we're doing the ones I'm highlighting. We're not including the last one. We're going from the first one to the n-1. So 0 to 4.5. We're leaving out the last one. Again, look at the picture, right? You don't end up using this last function value on this one. You only end up using it over here. Questions about what I'm trying to say there? I'm going to write this out still and kind of be as clear as I can about it. All right, so let's plug those numbers in. So delta x was 0.5. So 1/2. And then we add up all the function values except the last one. So 1, I think I might have enough room to stick them all in here. Let's see. If you get this, feel free to not write them all down, but it's a good idea to write them all down because if you get confused later, you can have these in your notes. You can look and say, what numbers did they use to get that? Oh yeah, I wrote it down. Right, so I'm starting at the first one, going to the second to last. Easy calculation, right? We're adding up a bunch of rectangles, but we don't quite use the last one. And so this ends up being 1/2 times 81.25. So this is an underestimate of the area. And we're just going to do the same thing, but we're going to do the right endpoints, right? And so the right endpoints is going to be the x1 all the way to the last one. Questions about the notation on this sometimes is the tricky part. Anything about that at all? Okay. So let's use right endpoints.
And then so we take the average of both once we're done.
If we wanted like a really great estimate, yeah, we could average both of them. Yeah, that is something I would point out. Exactly. Depends on the question, right? A lot of times these questions in the homework and what I oftentimes just do on tests is just say, just estimate it using right endpoints or left endpoints. You know, if we want the exact value or a really good value, we're just going to do the exact thing that we'll look at next time. Other thoughts before we keep going? So I'm just going to write this one out again. So the area is approximately delta x. And then instead of starting at 0, we're going to start at 0.5, right? Start at the right one. And we're going to go all the way to the last one. So f of 1 all the way to 5. Right, if we kind of highlight the area we're using these pieces. We're not using the first one. We're not using the 0, 1 piece. We're going the second half. We just plug the numbers in, right? And so it's going to be a bigger number. It's going to be an overestimate. So 1.25, 2, 3.25, 5. I'm going to tediously write them all out just because I love it. Just love getting this estimate. Oops, gotta write the correct numbers though. And so in this case, when you end up doing it, you get 53. Gosh, horrible. And so as John's pointing out, the real estimates, the real area means between the two of them. If you wanted a great estimate, you could average those two things. I'm not going to necessarily ask you to do that ever, but you know, it's at least noting that the area bounded between our function and the x-axis is between these two numbers. All right, great. Just looking at a few of the homework problems related to this while people finish writing things, and I think they're not too bad. Again, this is next week though, so no rush on that. There are a bunch though, so some kind of set it up for you, ask you to think about it. Some are asking you to do the whole thing, kind of like we're doing now. You know, when you use different functions, they have different shapes, and so different things happen. That's kind of what we're exploring in some of these problems. None of them look terrible though. Questions? So I just wanted to add those couple things that we said too that we're not going to get into the next section, but we've got a few minutes left, and it'd be good to talk about how we can improve this. Always good to think about how can we improve the estimate? Because, you know, thinking about how people actually came up with the exact value sometimes, they probably started with these estimate ideas and then thinking about how to improve it. And eventually you get something, you work towards the exact answer. Someone said, what's the word after area in the bottom thing? It says bounded. Yeah, I got to work on, when I get to the bottom of these pages, my hand slides off. Handwriting gets extra bad. Okay, so someone had said we could use a better method. And if, you know, if we, oftentimes this happens in high school. I feel like I remember in high school going into the trapezoidal rule. Is it trapezoidal? Now I feel like trapezoid method, trapezoidal method. Is anyone familiar with that method that can confirm that? trapezoidal method. I think there's an AL in there. And I would just encourage you to take a look. You just see Google if you wanted to look at that. But the idea is you have the curve, right? If we're trying to estimate the area under that curve still, trapezoids have an angled top. And so instead of just doing a rectangle like that, you instead connect those two pieces with like an angled piece. And so you just kind of get closer up to the graph, right? And so there's less error. That would be a rectangle. That's a trapezoid. Just kind of get closer up to the graph. And the other thing that someone has said was more rectangles. And that's a really key thing, because in the next section, we're going to talk about when you, well, let me just draw the picture first. I just love drawing these pictures. If I don't mess it up, this usually illustrates the idea. If you want to do the same kind of thing, but we only have a couple rectangles, we have big gaps there, right? But if we kind of stick more rectangles in there, we end up getting closer to the actual graph. Right, so there's some error. This one's going to have less error. And so what we'll see in the next section, if you kind of page to the next page, is if we take the limit as n goes to infinity, right? So we throw a limit on the expression we just dealt with, that implies there's somehow infinitely many rectangles, right? If we could stick infinitely many rectangles under there, whatever that means, we would get right up on that graph and we would get the exact number. And so I believe that's what it says right here, right? This is going to be, we'll see this next time. This is the exact area. And you can see it equals, if you take infinitely many triangles, rectangles, excuse me, I keep saying that. Yeah, somehow had infinitely many rectangles, we would get that exact area. And so that's how we usually bridge this concept with the exact area. This page is sort of summarizing where we've been and moving us towards where we're about to be. And the last section might have been a little confusing. And so what I like to try to start with is just a quick summary of that last section. And I'm going to delete this red stuff so I can have a little more room. So what I'm trying to do here is draw the same graph twice, and actually just going to copy this one. And the reason I want to draw the same graph twice is because I want to remind you about the difference between right and left endpoints. Because I tried to explain it last way in a way that derived the idea, but by the end of it, I worry sometimes that it wasn't as clear as I'd like it to be. So I'm going to sort of re-explain both those things and write their formulas down. And I think this is a nice way to sort of refresh ourselves or kind of summarize the things that are on the last couple pages. Right. And so remember, each one of these times, we're trying to estimate the area between 2 points. And so what if A was right here, and let's say B is right where this crosses the x-axis, right? So A and then B. And last time we drew rectangles. And so, but you know, the ones we drew rectangles on were all looked like this. I just kind of did a very simple function that was increasing. And so what happens if you have a function that's increasing and decreasing, right? It's like decreasing on this piece, but then it's increasing during the rest of the piece. How does that look? Well, it ends up being this way if you use left endpoints. So I'm going to try to do the same number of rectangles. Maybe I'll do 1, 2. Remember, the left side of the rectangles are going to be touching here. 3, 4, 5, 6. So trying to, again, the dots are kind of showing the left side of the rectangles are touching. And notice when you do that, it ends up being an overestimate in certain pieces and an underestimate in other locations, right? But if we use right endpoints, the opposite thing happens. So I'm going to do the exact same thing, but if we use right endpoints on that same interval, so let me break up the interval again. 1, 2, 3, 4, 5. We use right endpoints, all of a sudden it ends up being like this. So that one actually doesn't even go anywhere. Right endpoint would be right here. Right endpoint. Right endpoint. Right endpoint. Oops. Right endpoint. It ends up being a completely different picture, a different estimate when we use right endpoints compared to when we use left. And maybe let me try to emphasize the endpoints by making them a slightly different color. So the first one's a little funky because you don't even get anything on the first piece because it's crossing right at that location. Right. So we only end up with these ones. And then same with the last one. And so remember, the formulas for this are as follows. We're summing up function values in both cases. And so this part of it is the same in both cases. What's different are what I ranges between, right? So I've just written the same thing on both cases. The difference is in the first one, I goes from 0 to n minus 1. And in the second case, it goes from 1 to the end, right? But in both cases, you're just doing like base times height. Oops, it's height times base, really. Okay. Again, so this is just showing us when we have a curve that goes up and down, we get vastly different estimates when we do right and left endpoints. Sometimes pieces of it are overestimates, other pieces are underestimates, and it flips when you do the other version of it. Right? And this is perfectly fine. This was a nice sort of starting estimate. But the idea is, and the thing we came up with at the end of last class was, if we want a really good estimate, we would want to just put more rectangles in there, right? And the more rectangles you put in, the less error we end up with. To the point where if we want the exact value, we would want to use infinitely many rectangles. That's what sort of this is saying right here. If we let the n go to infinity, and n is the number of rectangles we have, we end up with the exact value between the 2 points. And so this is the new notation. The integral sign, this which looks like a big S, it means the integral from a to b of the function f of x with respect to x, right? That dx is the same notation we saw before, is thought of as having infinitely many rectangles underneath the curve, is how we're thinking about that. And so that's what we're doing in this section, is we're now, let me just sort of explain this, right? So this right here reads like this, right? The exact area between the function and the x-axis between the points A and B is given by this new expression, right? And this part of it is the integral sign. It means take the integral of this, just like when we do d over dx means take the derivative, right? That now I'm saying when you do the integral with it, which is the big S, it means do the integral. And we'll talk about what that means in a second. But it's just a new notation. Okay. So let me also write this down. I'm just trying to decide if I want to say this. I think I'm just going to write this in another way. So another way to say this notation would be to do the integral from a to b of the function f of x. And it tells us the area between the function and the x-axis, right? So if I put this, see if I can copy this thing again one more time. I've got my curve here one more time. The integral would tell us the exact value that we're looking for. So I'm going from A to B again. And now the integral is going to tell us exactly what we want. It's going to tell us this specific area. No rectangles, tells us the exact value that we want. That tells us that area. Any questions about what I'm trying to say there? No more rectangles, we get that exact value we want. And the key takeaway as you're finished writing this up is the way we do this is we need to know the antiderivative. And so that's where we're getting at the next page. So to evaluate this, we need to know what's known as the antiderivative of the function. And so that's what's leading us to the next page. What is the antiderivative? If we want to get this exact area between the function and the x-axis, how do we do that? And notice how it works, right? It's the area between the function. So if it's above the x-axis, it ends up being like this, right? But if the function's below the x-axis, it ends up being this piece. And so part of what I'm trying to just make clear is the area between the function and the x-axis. Like sometimes people think we're finding this area, for example, right? If you're not clear about what's going on, that's the area above the function, really, right? We want the area bounded between the function and the x-axis, which is this and this. It's another thing I want to make sure is clear. Okay, thoughts about that? Any questions so far? I'm going to talk about what the antiderivative is here, but I'm happy to clarify anything. Anything at all. Okay, so the question is, what is an antiderivative, right? If we want to do this, we need to know the antiderivative. Let me just page ahead. Okay, good. So here's a whole list of antiderivative rules that we'll talk about in a minute. Just like we had derivative rules, we've got antiderivative rules. But before we look at that, let's explore the idea, right? And the word antiderivative should have a specific meaning to you. And it doesn't mean that you hate derivatives, right? Sometimes people, I feel like, think, oh, antiderivatives mean I'm antiderivative. This is great. Hate derivatives, so I'm antiderivative. No, it doesn't mean we hate derivatives. It means the opposite of derivatives is the way you want to think about that. It means, let's read what it says right here, right? The antiderivative of a little function, and I'll refer to this as, I know it sounds weird, but I'll refer to it as little f, is a function capital F, which I'll often call big F, such that when you take the derivative of the big F, you get the little f. In other words, right, when you do d over dx of capital F, you get the little one. And so I'll try to differentiate big F and little f with capital, and then I try to do a little tail on the little one. Right, so you see how the word antiderivative makes sense? We're doing the opposite of derivative. We're trying to like think about, what did I take the derivative of that got me this, right? That's sort of the thought process. And so if we're looking at this first problem, it'd be really great if everyone just focused in and thought about this idea. If our little f is 3x squared, right, what is big F? In other words, we want to think about, I take the derivative of what to get 3x squared, right? That's what we're trying to think about. That's the notation I'm trying to sort of get across here, right? What do I need to take the derivative of to give me 3x squared?
X cubed.
Yeah, x cubed, right? So I'm actually going to erase the what part and put x cubed. right? Because it's like, oh yeah, you bring down the 3, subtract 1 off the power, and we would get 3x squared. And so this is sort of telling us that big F equals x cubed is an antiderivative of 3x squared. Because when we take the derivative, we get 3x squared. Okay, that's sort of the goal I'm trying to get across. But I'm also highlighting this word "and," right? It's not the only one. It's just one of the options. What are there other? What am I trying to say here? Like, what is another thing we could take the derivative of? Maybe that would also work. All right, what goes away when we take derivatives and just kind of gets lost?
Constants.
Yeah, constants just go away when we take the derivative, right? So if we had x cubed plus any constant, it would also, and we took the derivative, it would also be 3x squared. So let's write that down, and then we'll kind of build on this. So x cubed is not a unique antiderivative of 3x squared because x cubed plus any constant also works. And if that's still not clear, I'm just going to write down a couple examples and show you what I mean. So for example, capital F of x could be x cubed plus 2. Right? Capital F could be x cubed plus 100. Could be x cubed plus any constant, like, I don't know, pi, whatever. Right? If you take the derivative of any one of those 3 things, the constant just goes away and you get 3x squared, but each one's a different function. And so what we're trying to say here is these antiderivatives are not unique, right? So if I took the derivative of any of those 3 things on the left, you get 3x squared because the constant just goes away. And so if we're trying to recover the constant, we don't know what it used to be, right? And so that equals 3x squared for all examples on the left. And infinitely many more, right? You could add any constant on there. And so that sort of gives us the idea of, okay, antiderivatives are not unique. And so there's the idea of the sort of the antiderivative of the variable part, but then there's the family, which is now at the bottom of the page. The family of antiderivatives thinks about, okay, well, we need to put a plus c on the end of there because there might have been a constant there that we lost along the way. And so that's what this part says. This is the family of antiderivatives now, right? So when we take the integral of a little function, we do the antiderivative, then we also throw on a plus c is what this is saying. Right, so I'm going to write that down in words a little bit here. Excuse me. And also this is a good place to clarify this dx part. Don't get too overwhelmed by that or confused. It's just like when we do d over dx, for example, right? It just tells us the variable that's in there. This just means with respect to x. Just want to throw that on there. And so what this is saying, this notation, we want to be able to read this stuff, right? This is saying when we do the integral of little function f, we get the antiderivative, which is capital F. But then we also do plus c for any constant that we lost along the way. So that's why I think about a list. For any, we gotta think about it for any constant that existed before the derivative. Right, we're trying to undo the derivative, antiderivative. So what, this whole page is trying to say, well, if we had a constant there, it's just lost. We can't figure out what it is. I mean, there's ways to figure it out, which we'll talk about in a little later. But for now, we just put a plus c to represent that. Okay. Thoughts about what I'm trying to say about difference between an antiderivative and the family? Okay, so what is the antiderivative then? How do we figure out what that is? Let's keep moving forward with this. So what I'm going to make the note here is see the next 2 pages for common antiderivatives. And I'm going to go flip into that. The antiderivative of this function. And so let's look at the rules that apply before we do that, okay? So I'm going to go to the next page here, and here are all the rules for antiderivatives. And you can see, if we kind of figure out, look at this page and think about how it works, A and C are all going to be constants. So like here's a constant. These are all constants, right? Is there another A in here somewhere? No. So that's the only A, right? So the things I'm highlighting, or I'm close to highlighting, are just constants. And what the way this is working, it's telling us when you have this kind of functional form, the antiderivative is this, right? And then we think about this part as being the family of antiderivatives. And so the difference between this and this is just a plus c. Right, you see that? It's literally the same thing, and all this is just you have a plus c over on the right to represent the family. Right? And then I would also point this out. In all the cases here, we have little f being the function and big F is the antiderivative, right? So this is a thing you're given usually, and this part is the antiderivative. Okay. And so the way, the nice thing about this is it's like, oh, a bunch of things we need to memorize. How are we going to do this again? I already memorized all these other things. All these rules are just the opposite of the derivative rules. So we already know them, right? Like look at the first one. Look at this first one. I'm just going to circle in green. I like to call this one the anti-power rule, right? When you do the power rule, you bring down the power and multiply it and subtract 1 off the power, right? This is the opposite. You add 1 to the power instead of subtracting. And then instead of multiplying by that, you divide by it, right? Literally just doing the opposite, right? Look at the constant rule, right? Usually when you do d over dx of ax, you get a, right? The x goes away. And so here we're doing the opposite. We're starting with the a and we're going back to ax. And that's what this says. When you start out with a constant and you do the integral, you just throw an x on top of it. Right? So we're undoing the derivative rules. E to the x is the same, right? When you take the derivative of e to the x, it stays the same. That means when you integrate it, it also stays the same. Right? So we already know these rules. This is the thing I would really just emphasize is we're doing the opposite of the derivative rules. Now, some of them are a little funky, like ln, because we didn't really have, when you think about the derivative of ln, it becomes 1 over x. And so we have that rule right here, right? Because we know when we differentiate ln, we get 1 over x. And so we're doing the opposite here. When you integrate 1 over x, you get ln. So that's different than the ln rule. This ln rule, and I would say this rule doesn't come up a ton. Notice the sine and cosine rule, right? The derivative of sine is cosine. That's from the derivative section. That means when we integrate cosine, we get sine. Right? And that's what this one says right here. So yeah, I don't want to spend a ton of time in these rules because we already know them. I'm just trying to point out how we're thinking about it. We're doing the opposite of derivatives. Can I clarify something about that? And then to see how we have the regular one in the middle and then the family on the right. And literally it's just throwing the plus c on here. That's the only difference. So let's look at that first example. The first example is this one, right? We've got a bunch of anti-power rules, quote unquote. And so we're going to add one to the exponent. Oh, I can't really put both those. I guess I could do this, right? This one right here is just an application of this. Add one to the powers, put on the power. Oh, and then the one on the end is a constant, right? This one is going to be the constant rule. With me on that, I'm going to erase those colors in a second there, but just kind of identifying what rules we're going to use in a second. Okay, so let's do that. And I'll write out the details on this first one, of course. So let's integrate g of y dy and start using that notation. Squiggly s thing means integrate. Dy means y is the variable we're going to use, right? And so this becomes this. Okay. And we're going to use those three things I just talked about. Oh, I guess I should mention this too, right? Let me go down to the rules again. We also have, I forgot the rules at the bottom, what to do when we have constants and what to do when we have sums. And it's the same thing with derivatives. Remember, with derivatives, you just kind of do them separately. And that's what this is saying. It's like, hey, when you integrate h plus g, you just get big H plus big G. So you just do them separately, right? When you have a constant, you just ignore the constant and you just integrate the function. Same kind of idea as derivatives, right? So on this one, even though we're integrating three separate things, you just do them one at a time. And really the 2 kind of just comes right out in front. We actually ignore the 2. So let me do that too. Right, just being kind of real careful. When you have three separate things, just do them separately. And then we do the quote unquote anti-power rule. And so here's what that looks like. Add 1 to the power, divide by the power. Right. And I'm going to do this one time. And then we put a plus c. And I'm only going to do it this way once, and I'll explain what I mean in a second. And then we add 1 to the power, divide by the power. And then we have a second constant. And then the 1 becomes a y, that's the constant rule, plus c3. And so here is our simplified derivative. And instead of writing three separate c's, we just kind of think about them collapsing into a fourth c. And so I don't need people to do this in practice. But what I'm trying to say is when you think about them individually, they each get a plus c, but then those collapse into this fourth c. And so really you only need to add on 1 plus c, right? So I don't need to necessarily see that. What I'm trying to say is each one gets 1, they collapse into 1. And so really the way you would want to write this is y cubed over 3 plus y squared plus y plus some generic c that accounts for all of them. All right, and that's our first antiderivative. That's great. Let's pause there and see how that looks. clarify anything there? Okay. So we're really, we've only looked at the first couple rules, and the third one's pretty straightforward too, right? We haven't looked at it, but that's pretty easy. We'll get into some of these more complicated ones as we move on, and then you can see down at the bottom here. Where am I looking? Later on, I'm just going to kind of flash ahead just for one quick second. We'll talk about doing more complicated ones. So eventually we want to think about undoing the chain rule, right? This is the chain rule being shown right now. And to undo the chain rule requires some more advanced methods. So we're eventually going to get to that. But let's do some more sort of more basic ones first, quote unquote. So no questions about this one? Is everyone all set with that? Can I keep going? I don't want to move it too quick. Okay, so let's do another quote unquote simple one, right? So we have these couple integral properties. The first one says, and I just used it a second ago, right? If you have something like 2x dx, you just ignore the 2 and you just focus on the x, right? I just did that one in a second ago. And we just did this one too, right? If you have like x plus 1 and you want to integrate that, that's not any more complicated than just doing them separately. Right, and so let's do that on this first problem. Right, so when we do this one, we just we just think about them separately, add 1 to the power, divide by the power. Right? The 2 is a constant, the 2 just gets the x, right? This is the constant rule. And then we throw the plus c on it. Now, the cool thing that, I don't know, maybe cool isn't a stretch, but the nice thing about these, and I guess maybe we should simplify it, 2 is divisible by, or 4 is divisible by 2. The nice thing about these antiderivatives is we can always check our work, right? Because we know how to take derivatives. And so we can always just check to see if we got the right answer by just differentiating this thing. And I would never sort of ask you to do that in a test or anything, but it's a good mental check, right? And this is an easy one to do, especially if it's a power rule. You can just look at it and say, if I take the derivative, do I get back to the original? Let's see, right? Bring down the power, subtract off the power. Sorry, that should be an x. Okay, yes, we got back to the original. So that makes me feel good. So that is the answer. All right, what do you think? Is this okay? You guys kind of understand the idea here a little bit?
So in 2 dx, instead of just, because like since there's a constant rule in the derivative, it would be 0. So instead of being 0, we just add an x.
I'm sorry, can you say that one more time?
Like, you have the constant rule for 2. But if you were taking the derivative of it, it would be 0. Since it's the opposite, you just add an x instead of converting it to 0.
Yeah, so what you're saying is when you take the derivative of 2, you get 0.
Yeah.
That's why when we integrate nothing, we do a plus c, because we don't, the 2 just goes away. And so when we integrate nothing, we don't know that it used to be a 2. So we just do a plus c, where c is any constant.
Mm-hmm.
Now, if we differentiated 2x, the x goes away and we just get 2, right? Is that okay?
Yeah.
And so that's why if we integrate just 2, we get 2x. Now we put the plus c on there because there could have been a constant, but we're thinking about going backwards from the derivative. Like, what did we take the derivative of to get to is the way we think about that. And we think, oh yeah, there used to be an x to the 1.
Okay. Thank you.
Yeah, other clarificational thoughts? Thank you for that thing. So, my goal here is actually just to let you think about the rest of the ones on this page. And I didn't specifically talk about the rules, but you can look at the rules, right? We know the rule for the sine functions right at the top there. The rule for e and tangent are right at the top there. And so I would ask you to think about those. Let me set this one up, though. Remember, how do we do ones like this with derivatives? What was the sort of the approach? Remember? If we differentiate radicals or 1 over x squareds, how did we do that in derivatives? Anyone? Right, like if this didn't say integral, if it said d over dx, what would we do? Did it a whole bunch of times. It was on the test. Pretty sure people know how to do that, I think.
Set it as x to the 1/2.
Yeah, we make them exponents, right? We make, so x cubed is an exponent, but the square root becomes 1/2, right? The x to the -2, or x squared, excuse me, becomes x to the -2. And so we would do the same thing here. We think about this as x to the 1/2, x to the -2, and then use the anti-power rule, quote unquote. Right now, each one of these things looks like this, right? So add 1 to the power, divide by the new power. All right, take a second and explore this a little bit. So try this one, 1, 2, 3. Take a look at the rules. Don't forget to add a constant, right? So you're going to throw a plus c on there. Now is a good chance to just sort of get your hands dirty right away with some of this. It's new stuff, but it's stuff that you should be familiar with because we know the derivative rules, right? So just do the opposite of those rules. And if that doesn't make sense quite yet, just use the references up here. Right, so here's how you do tangent, for example. E to the x stays the same, etc. Just give you a minute to do that. I've also realized too that these are an opportunity if people have a question and they want to just, like, if we were in person right now, I'd be walking around the classroom sort of giving people one-on-one help. If people would like that one-on-one help, we can do a quick breakout room. I've sort of really recently realized. So anyway, I could do something like this. I could like open up a room, and then if anyone wanted to talk to me, they could like pop into the breakout room. Anyway, just an idea there if you wanted some sort of one-on-one help in these strange times. Maybe I'll start writing down a few details here. So So on this first one, we just add 1 to the power. Oops. Divide by the power. Add 1 to the power. Divide by the power. Add 1 to the power. Divide by the power. Throw on that plus C. And then when we divide by that fraction, man, that's horrible. And then we've got the -1 in the bottom, so this can be simplified a little bit more. Could be x to the 4th over 4. Remember, the 3/2 becomes 2/3 and multiplies. Then when you divide by -1, just makes that thing negative. So here's a nice simplified version of that. What do you think? Is that okay? You know, the sine and cosine ones are ones that trip me up pretty regularly. The only thing I ever remember is that the derivative of sine is cosine. And using that, you can kind of reason through the other ones, but it still doesn't stop me from messing things up. So anyway, just using those rules, right? Sine becomes minus cosine. And we do the plus C. And again, you can always just like double check that, right? Like, does that make sense? If you've got the derivative rules in your mind pretty good, if you differentiate minus cosine, cosine becomes minus sine, right? So we have like minus sine. Yes, the minuses cancel and we get back to the original. Okay, good. Right, just a quick mental check is helpful. Tangent's a weird one, right? That's definitely not one that I have committed to memory. It becomes this, right? It's a little bit strange. But we just apply that. E to the x is one of those nice ones, right? It just stays the same. E to the x doesn't change, or e to the t in this case. And then we end up with a double negative. We have like minus, and then tangent becomes minus ln, absolute value of cosine. And so the double negatives become a plus. All right, what do you think? All right, I'm gonna write one more down here just so I'm just kind of looking at the list and seeing that we don't have one for ln. So what if we integrated, let's do another root one. How are we doing on time? We're doing great. All right, so we have that root, right? Cube root of t squared becomes t to the 2/3, right? And notice how 1 over t, if you tried to think about the integral of 1 over t and you were thinking about that as t to the -1, right? Then adding 1 to the power would be 0. And then dividing by that, oops, that's no good, right? So that's why the integral of 1 over t is the one case where you don't think about it as a power. Instead, we think about it as being ln, right? And we know that when we take the derivative of ln, it becomes 1 over x. And so that makes sense. We're undoing that. Right? And so 2/3, add 1 to that. 1 plus 2/3 is 5/3. And 1 over t becomes ln. And of course, we shouldn't leave it like that. So this becomes 3/5. Okay. Hopefully we feel good about these kind of basic ones.